Okay, now we're going to look at this region here. We're going to look at the Bowman's capsule. And we said that ultrafiltration is what happens here. Now, Bowman's capsule is this part here, and we've got blood flowing into here through the afferent arteriole, and when it gets in there, it basically coils up, so you get this real network of blood capillaries in here, and there's a lot of coiling and folding. Okay, and then they join up to form the efferent arteriole. So this is called the glomerulus. I'm gonna just get rid of this bit for now. The blood flowing in here is under high pressure because it's not that far from the heart. The blood leaves the heart through the aorta and travels a relatively short distance until it reaches the renal artery, and then once it gets into your kidney, it splits up into arterioles. So we've got high pressure, high hydrostatic pressure because of its proximity to the heart, the relatively short distance it has to travel. The fact that this afferent blood vessel has a much larger diameter than the vessel that's taking the blood out, the efferent arteriole, means you're going to get a big build-up of hydrostatic pressure in the glomerulus. And finally, because of these blood vessels coiling, that's going to restrict the blood flow and create a bigger pressure. So those three factors mean that we've got a very high hydrostatic pressure inside the glomerulus. Now, the glomerulus is a blood capillary. What did you learn about the structure of blood capillaries in lower sixth? You learned that the wall is only one layer of cells thick, and the walls are made of the squamous endothelial cells. So a capillary, if you were drawing a capillary, you'd probably draw something, a cross section might look something like that. Okay, so you have a number of cells, but it's only one layer thick. And so in between these cells, there will be tiny little pores. And that's okay most of the time, but if you turn the pressure up, it's a bit like if you've got a hose pipe and you've got a few pin pricks, a few holes in the hose pipe. If you have a low pressure of water flowing through, it's fine, you don't notice it. But if you turn the pressure up really, really high, you're going to see water spurting out of all those little holes. And that's what happens in here. When the blood flows into the glomerulus, it's under really high hydrostatic pressure. And so the liquid parts of the blood will start to get forced through these pores and move into the space here. Now, the barrier then, if we just look at, say we've got a bit of a capillary here, okay? If we look at this bit here in much more detail, I'll wipe this out here. So we've got cross section, there's the blood flowing through there. So these are if we've cut through the blood capillary, these are the walls at the top and the bottom. The cells are squamous endothelial cells, and there will be tiny little pores in between some of them. So when you've got high pressure, fluid can be forced through that pore. Now, there's another structure that you probably don't know about, and it's really like a mesh of fibers called the basement membrane. And it really acts like a sieve. Okay, so we've got pores here in the squamous endothelium. The fluid will pass through there, and then it will reach the basement membrane. Now, what's the fluid part of blood? Well, we know that blood is made up of red blood cells and white blood cells. They are too big. They're not going to get through any of this. So they will stay in the blood. So we've got plasma. So most of the plasma will get through here and will also get through the basement membrane. Think of the basement membrane as a really fine sieve. So it's going to let things like glucose is a small molecule, it'll get through. Glucose, water's a tiny molecule, so the water will get through very easily. salts, magnesium, phosphate, calcium, all those kind of things will also get through because they're tiny. Now, there are also proteins, things like hormones and so on, fibrinogen and stuff like that in the blood plasma. So the plasma proteins are big molecules. Proteins will not get through. So the basement membrane really is the filter. It's effectively the filter. It does the filtering. So blood cells won't get through, and proteins are too big to get through. But the kind of things that can get through are, well, water, glucose, amino acids, urea. Urea, you may remember that when you eat proteins get broken down into amino acids. The amino group gets removed in your liver and it forms a substance called urea. Urea is toxic. Now, in tiny quantities in your body cells, it's fine, but your blood has to carry it to the kidney and it needs to get filtered out of your blood. So at this stage, yep, urea will pass through here. So urea and then salts. All those kind of molecules are tiny. They will get through here. So it's called ultrafiltration because it's only tiny little holes in the basement membrane. Ultra means really small. Okay, so where's the next layer? We've got the squamous endothelium, we've got the basement membrane, so that's part of, those two are part of the capillary wall. And then we've got the Bowman's capsule, that's the next layer. If we just look at this diagram here, or in fact, if we look at the one in your textbook, this is the glomerulus, we've got the Bowman's capsule. So the layer of cells here lining the Bowman's capsule are called podocyte cells. And they've got this unusual thing. They've got these projections that come up at different angles. And there's basically filtration slits. And the fluid can get through there and get into the Bowman's capsule. So we've got the podocyte cells. And then we've got the Bowman's capsule underneath here, like the actual cavity here. So there's three things. We've got squamous endothelium, we've got the basement membrane, then we've got the podocyte cells, and the fluid gets through all those and into the Bowman's capsule, and now it's called filtrate. So that's how we've got this high pressure forcing the fluid through. We've said it's the plasma minus the proteins, and the blood cells are too big as well. So proteins, blood cells too big to pass through the filtration system. And the actual filter itself is the basement membrane. It's really like, if you think of a sieve you'd use in the kitchen, yeah, that's what this is like. Now, we've talked about the really high hydrostatic pressure that you've got. Now, if I just rub this out, whenever you were studying lower sixth work, you talked about things like water potential and osmosis and solute potential and so on. So the hydrostatic pressure we've been talking about is really the pressure potential. If you think of the blood flowing here, we've got, so blood, and then we've got Bowman's capsule. So here's the Bowman's capsule. The blood is under very high hydrostatic pressure because of its close proximity, the short distance from the heart, because the afferent arteriole is much wider diameter than the one leaving it, the efferent arteriole, and also because of the coiling of the glomerulus slowing down the speed of the blood, and that creates a higher pressure. So we've got a very high pressure potential. So if you think pressure potential, solute potential is due to the solutes in the blood, so due to things like the glucose and the plasma proteins and so on. Water potential is equal to the solute potential plus pressure potential. You should remember that from last year. Now, So if we just pluck some figures out of the air, very high pressure potential in the blood. Bowman's capsule is going to be much lower, because remember, the blood has just come from the heart, and we talked about the diameter of the vessels and the coiling and so on. So it's going to be very high. It might be about 1. The textbook gives you a figure of 1.4. The figures are only for illustration only. You're not expected to learn any figures or quote any figures. If there was a question about it, they would give you the figures and ask you to work it out. So much higher pressure in the blood than there is in the Bowman's capsule. In the blood, we've got a lot of plasma proteins, and so that makes our solute potential much lower. So our solute potential here, again, your textbook has it being minus 3.5 for the solute potential. Bowman's capsule doesn't have proteins. Yes, it does have things like glucose and stuff like that, but it doesn't have all the proteins and all the stuff that the blood has. So the solute potential in the capsule, Bowman's capsule, is going to be much higher, much closer to 0. And so your textbook gives it a figure of minus 0.7 kilopascals. So what's the water potential of the blood? Well, it's the solute potential plus the pressure potential. So if we add these two figures together, remember that's a minus figure, you get 2.0 kilopascals as the water potential of the blood. So minus 2.0 kilopascals in the blood. The glomerular filtrate, the filtrate that's got out of the glomerulus into the Bowman's capsule, well, if we add that to that, it's minus 0.7. Actually, I've done this all wrong. I don't know what I'm like. My maths isn't working too well at this time of the night. So that's not minus 2. It's actually positive 2 kilopascals. This is 0.7 kilopascals. So 2 there, 0.7. Think of osmosis. Osmosis is movement of water from a high water potential to a low water potential. So water is going to move in that direction. So that's what we call the filtrate pressure. The net filtrate pressure would be the difference. So it's going to be 1.3 kilopascals, 2 minus 0.7, 1.3 kilopascals. That's your filtration force, and that's forcing the fluid from the blood into the Bowman's capsule. So hopefully that makes sense. But sit and have a good read at your textbook. Drop me a private message or email me if there's anything you're not sure about, and we can go over it again. All right, thanks very much. I think it's time I went to bed because my brain stopped working. But at least you didn't have to look at me this time in the video, so that's good. All the best.